Welcome back to another final installment of these videos.
Yeah.
We're gonna get started to finish. It's been a long and arduous journey, but we're ready to finish it out strong. So, for number 1A, the chart looks like this. So you'll have to take a look at that later and make sure it's all right. B, E. coli DNA polymerase 1 would denature at such high temperatures and not function. C, the helicase from E. coli would denature and have no effect on the reaction. D, the three tubes without the DDGDTP, DDCTP, and DDTTP will not truncate, and therefore only the gaps will be shown on the gel for the adenine gaps will be shown on the gel for the adenine tube.
Yeah. All right, so number 2, for A, we got the Taq polymerase synthesizing step. Wasn't sure how to summarize that super well. For the second part of that, we got the primers annealing to complementary sites on DNA step, also a mouthful. B, we got AMP-R and restriction endonuclease. For C, we got to the positive end. For D, the 2' hydroxide group and the 3' hydroxide group. And E, transformation, F, IPTG, and XGAL. And on to number 3.
Okay, so for number 3, we had to figure out the primers. There's 4 different options, but we chose the ones that would allow you to add from the 3' end. So from left to right on the top, and from right to left on the bottom. Also written out here. And so that's them, and then we found out we plugged in that 57% of it is a G and a C in the primers for both of them, and we plugged it into the equation with 16 base pairs, and we got 39.55 degrees for each of those on part B. C, you just had to draw out or write out what it would the complement would be on both sides, and then if it was getting truncated at all the cytosines, you just stopped it at each cytosine, so each fragment would stop at the cytosines and get smaller and smaller. And then D, because the strands are being denatured in order for DNA synthesis to begin in the this method, you don't need the DNA and DAM are not necessary because it's already like denaturing and spreading apart instead of it doesn't need that other processes to function. So yeah.
Cool. So 4 is just kind of mostly the drawings. For part A, we just literally drew out all the different base pair lengths, as you can kind of see in the camera. And yeah, I mean, it was pretty straightforward. You just copy and paste over from the chart that we have. And then for part B, we just do that in a linear model. And so you can also see what we did there, if I can hold it right. We drew the sample here. Oh, never mind, we didn't do the sample on this, but the map here is on the bottom, which is what we used to answer part C. And so basically what happens if we were to, if we cleaved all three of the molecules simultaneously, we'd expect there to be a split at each of these locations that we had here on the map. And so that's pretty much just the nitty-gritty of it. It's probably just best to look at it because you can't really tell in the video what we did very well.
Yep. So this was quite a process in order to do for question 5, but I'll just keep going. This is first, number 1, purify mRNA from a sample of the Saccharomyces cells containing the YFG gene, or your favorite gene. Mix the mRNA with a primer. 3, add reverse transcriptase and DNTP to synthesize DNA. Add RNase H, non-specific endonuclease that recognizes RNA-DNA hybrids to digest the majority of the mRNA. Add a DNA polymerase 1 or 4 or 5 is add DNA polymerase 1 from E. coli to synthesize a second DNA strand. 6, plasmid and chromosome DNA molecules containing the your favorite gene are digested with the restriction enzyme. 7, the cleaved plasmid and chromosomal DNA molecules are mixed. The plasmid sticky ends hydrogen bond with each other. Chromosomal DNA fragments that do not include your favorite gene, and the your favorite gene is inserted into the vector. Then 8, DNA ligase is added. 9, transformation of the E. coli cells. So the DNA is entered into live cells. The growth of bacteria on a medium that contains ampicillin with IPTG, and with ITPG, then it will metabolize the X-gluline, glen X, and if the colony is blue, it does not have your favorite gene, and if the colony is white, it does contain your favorite gene.
Do you know what time it is, James? Anyways, for number 6, do you hear that?
For sure. Are you guys recording?
Yeah.
It's okay, whatever.
Anyways,
being fun.
it is the final countdown, the last question of the semester for these videos. So, for CRISPR, it stands for clustered, regularly interspaced, short palindromic repeats. Say that 10 times fast. Yeah. And basically what that is it's a family of DNA that's found in prokaryotes, and it basically remembers viruses when they come. It like copies their DNA, and so you can use it together with the Cas9, and you can use it to edit genomes within the DNA. So it allows you to remove part of it and put in a new, different piece. And so it's pretty cool. They're trying to see what they can do with DNA in the future and customizing and editing it. So that's kind of cool.
All right. Thanks, Mr. Mills, for a great class and semester. Bye.